Good day, my name is Vitor Figueiredo Ventura and I'll present the impact of the heat transfer coefficient of the external medium, correction of the viscosity and pressure drop on a simulation of a restart using OPENFOAM. This presentation will follow this summary, introduction, methodology, case study, results and conclusion. Stops are very common in oil production. They can be due to emergencies or due to maintenance. In case of wax crude oil, the oil passes through a process of gelation, and this gelled oil is very difficult to characterize because the properties depends on a lot of factors like initial temperature, final temperature, shear rate and others. In this context, viscoplastic models are commonly used. Normally you use or a viscoplastic model or a elastic viscoplastic model. In my case, I will use a viscoplastic model, and numerical studies are very important in this area because, as I said, this gelled oil is difficult to characterize, so works on models and conditions behaviors are being developed, so it's much easier to adapt a numerical study than it's to adapt a practical study. So the objectives of this work is to develop a solver, implement a viscosity model, make simulations of all the process of restart. When I say all the process of restart, is the normal function of a pipe, the cooling process and the restart, and evaluate the impact of changing some parameters. I had to implement a third type boundary condition. Third type boundary condition is not implemented in OPENFOAM, but there is a boundary condition called mixed boundary condition. This condition asks for three factors: a fraction, a fixed value, and a fixed gradient. So you can rearrange the third type boundary condition to make a parallel between these two boundary conditions. So if you make the fraction a function of the heat transfer coefficient, the size of the cell of your grid, and the conductivity of the fluid, makes the fixed value equals to the temperature of the bulk of the external fluid and the fixed gradient equals 0, you can simulate a third type boundary condition for the temperature. I used as a base for my solver the solver OPENFOAM that is native to OPENFOAM. This solver uses the pimple cycle. Pimple cycle is a mixture between the simple cycle and the piezo cycle. It has a loop to solve the pressure velocity coupling and an external loop. In this external loop, I put an energy equation, the energy equation that's shown in the slide. And in this external loop, I put an evaluation of the viscosity. So my solver would enter this external loop, evaluate the viscosity, solve the velocity pressure coupling, and then solve the energy equation and repeat the loop. There was two conditions to exit this external loop. One was the maximum number of iterations, and the other was a variation of the viscosity. So if the variation of the viscosity was below a threshold in every cell, the simulation would continue to the next time step. But if the variation of the viscosity was higher than this threshold in any cell, the loop would repeat. The viscosity model that was implemented was a Harshal-Butler model, adaptation of the Harshal-Butler model. There was two variations that were made. One variation is it was added extra term. This extra term is to guarantee that the viscosity wouldn't drop below a certain value even for a high shear rate. And the other variation is that some terms are dependent of the temperature. The yield stress and the K were only non-zero below a certain temperature. So above this temperature, the fluid would behave like a Newtonian fluid, and below this temperature, the fluid would behave like a viscoplastic fluid. This is the flow curves of the viscosity model. As you can see, above a certain temperature, the viscosity is fixed, is a constant for each temperature, but below a certain temperature there is a non-Newtonian behavior. The case study was a 5 meters long pipe that has 10 centimeters of diameter. There it was applied a pressure drop. The pressure drop was calculated by the formula in the slide. The formula is function of the yield stress. I applied, in fact, a pressure a little higher than this formulation calculates, but it was to guarantee that the flow would occur. And here are the parameters used. In the left column is the parameters used in the simulation of the normal function of the pipe. The middle column is the simulation of the cooling process, and the right column is the parameters used in the restart simulation. The normal operation simulation would consist in applying a pressure drop and waiting until the steady state was achieved. The cooling simulation was made making the velocity equals to 0, so it was an abrupt stop. But for as my fluid is incompressible fluid, it was acceptable behavior. And the cooling simulation used as initial condition the final condition of the previous simulation. And for the restart simulation, a pressure drop was applied again, and the start of the restart simulation, the initial condition for the restart simulation, was the last condition of the cooling simulation. In all three phases, in the normal condition, the cooling, and the restart, were used two different heat transfer coefficients, and for the restart simulation, only the last phase, two more variations were made. The maximum number of iterations to correct the viscosity were changed, and it was used two different pressure drops. Here for the result, two things about this figure. First, the size of the tube is not in scale. It is a 5 meters long tube and 10 centimeters of diameter. So if I use the figure in scale, it would be very hard to see. And the other thing is the figure is only half of the tube. So the higher part of the figure is the center of the tube, and the lower part of the figure is the tube wall. Here is the temperature field for two different heat transfer coefficients. We can see that for a higher heat transfer coefficient, the fluid gets colder faster. It makes sense because this heat transfer coefficient is for the external fluid. Here are the velocity fluid for the two heat transfer coefficients. You can see that for a higher heat transfer coefficient, the fluid got a little slower. And here are the viscosity field. There is a V-shaped boundary between a region of high viscosity and a region of low viscosity. This occurs because as you approach the tube wall, occurs two things. One is the temperature drops, and the other is that the shear rate got higher. So the temperature drops tends to make the viscosity higher, but the shear rate going higher tends to make the viscosity goes lower. So these two effects makes that the viscosity has these two regions separated by a V-shaped boundary. Here is the cooling process for the two different heat transfer coefficients. We can see that for a higher heat transfer coefficient, the temperature got lower faster, but the two simulations are similar. And here is the restart simulations. Here for two different heat transfer coefficients. So the base case is got a lower heat transfer coefficient. We can see that the two simulations are similar, but looking for the last time that was presented, we can see that for a lower heat transfer coefficient, the region of high viscosity got much thinner, much more close to the wall. Here is the result for two different pressures. The base case has a higher pressure, 10 times higher pressure drop. So we can see that for a higher pressure drop, the restart occurs much faster. But one thing that you can think is that for a 10 times higher pressure drop, so it's a 10 times faster simulation. It's not like that, because as you can see in the last time, there are a region of high viscosity and a region of low viscosity, but the boundary between these two regions got much blurrier as the time passes. So it's not like it's only a 10 times faster simulation. No, this boundary between these two regions got blurrier and blurrier. And at last, for the variation of the maximum number of iterations to correct the viscosity, the two simulations are almost the same. If you adjust the scale of the figure to see inside the region of high viscosity or inside the region of low viscosity, you can see that there are fluctuations inside these regions. So if you look at the two simulations inside these regions, the fluctuations are different, but when you adjust the scale to see the whole process, the differences disappears. So for the conclusion, a solver and a viscosity model was implemented in OPENFOAM. Simulations of the normal operation, the stopping and restart were made. Changing of the heat transfer coefficient were made in all the stages, and in all the stages it was relevant. Increasing the pressure drop, increase the speed that restart occurs, and the number of iterations to correct the viscosity is not really a factor. Here are the reference used in this work, and thank you.